chapter is traveling waves and sound. By the way, in case you didn't get it from chapter 14, a lot of our heavy mathematical equation stuff has kind of passed us by. We're beyond that. We're more a lot of conceptual, very much applications. I mean, as if all that other stuff about acceleration velocity wasn't. Momentum. But we're going to explore the properties of traveling waves, do some kind of neat stuff with that. We'll learn about the wave model, which describes everything from earthquakes to sound waves to light waves, and everything in between. Okay, so lots of really applicable stuff here. We will talk about the intensity, which is how strong the wave is. So we already kind of hit on this a little bit, but here's the big idea here. Waves carry energy. Okay, it's sort of like I said, like y'all were sending a message to one another. Okay, well, it's sort of like but the message was energy. Okay, we'll talk more about like the period, the frequency, the amplitude, and how all that affects, for instance, louder sound and its amplitude. All right. So the wave model is the description for what we use to refer to this thing that we observe called waves. All right. And it turns out there's a lot of different things that act they all have the same property. Okay. And they all act the same way, and so we call those waves. A traveling wave, this is your official definition, is an organized disturbance that travels with a well-defined wave speed. Okay, so imagine when y'all are seeing out there that wave was moving along. Okay, would you say that it was organized? When like Kevin would whip it up there and go, and it would travel along the rope, organized? Yeah, because it wasn't random. Okay, it was obviously going up, then this part was going up, then this part was going down, and this part was going down, and this part was going up. See what I'm saying? It was organized. It was a disturbance. That string wasn't just sitting there. It was moving, okay? Even with the slinky in the spring, it was moving back and forth, and it traveled with a well-defined wave speed. We had some issues out there with some friction that was constantly slowing it down, but if we had a better setup, then we could measure it and do all sorts of fun stuff like that. What we're mostly going to be talking about right now are mechanical waves. That's when you've got the motion of the substance and you've got a medium. Okay, so you've got a disturbance here. We can see it moving up and down as it passes through. The idea here is it says a disturbance is a wave that passes through medium, displacing the atoms that make the medium that make up the medium from their equilibrium position. So they're being disrupted from their equilibrium position. But then, just like all that other stuff that we saw before, there's going to be forces that are going to bring them back down. There's going to be a restoring force pulling them back to equilibrium. In the case of the string, it's going to be that tension. In the case of the spring, it was the coils of the spring wanting to be pulled back. A wave is created by a source. Once created, then that wave travels, and you've got the wave speed. This is the huge idea, which I feel like we pretty much have a good handle on. A wave does transfer energy, okay? But the medium as a whole does not travel, okay? In other words, we got a message from Bell moving the rope or the spring, whatever, sending it down the hallway over to Binjay, but that whole rope wasn't moving and transferred. Does that make sense? Those little pieces of the rope went back and forth, but pretty much the idea was the energy was transferred, okay? So that's the idea. The energy is transferred, but the medium itself doesn't travel. A wave transfers energy, but it does not transfer any material or substance, okay? So we're not actually moving something from here to there. I can't say that enough, but whatever, I'll probably keep saying it. Electromagnetic waves are part of the electromagnetic field. This includes light waves, radio waves, microwaves, X-rays. It's a little bit advanced for us to talk about what's moving in that sense. We talk about that next year if you stick around for engineering. But here's the crazy part. Electromagnetic waves, you might be like, what's moving? Is it the air? No. Is it like something else? No. Electromagnetic waves, they can travel through a vacuum, okay? Which is good because that's how we get the light from the sun. They travel through the vacuum of space, okay? So it's a little bit more to it with the electromagnetic waves. There's also matter waves, which if you are read anything about quantum theory, everything behaves like a wave. That's more, we're going to talk about that at the after the AP test. But just so you know, there are other waves besides these mechanical waves. There's sound waves, which are mechanical waves, but the electromagnetic, the EM waves, and matter waves. We're not going to be talking about those too terribly much. So we saw transverse wave. You move it up, down, but the wave moves to the right. A longitudinal, you move it back and forth, the wave moves back and forth. So you can see that the motion of the wave is the same as the direction of that disturbance. Okay? With earthquakes, you get P waves, where it's like the earth, gets crunched and pushed here, and so you get this compression moving along the ground. This is what causes the real damage. It's the S waves, is when the ground actually is moving up and down. Because what happens is that the foundation, gets, messed up majorly as it cracks and breaks, and the building falls down. Okay? So you may say, well, what causes that wave to travel through the rope? And the answer is stuff that we already know about. Tension, forces, gravity, spring force, okay? All of those properties of the spring or of the rope are what causes the rope to act in this manner. For instance, if we were to isolate one point as this wave is coming along, we would notice, and we did the free body diagram, that there's more tension going up at this angle. There's also tension of this particle, this piece of rope, pulling this piece of rope this way. However, the tension is more in that direction, which is going to cause this to move up. Okay? And you say, well, why is this being pulled more that way? Well, because the piece right over here was being pulled more that way than this way. And why was this one being pulled more? Well, because this piece right here next to it was being pulled more that way. Do you see what I'm saying? So you go back and eventually you say, well, why did this piece get pulled more this way than this piece? And the answer is because Kevin lifted up on the rope. Okay? Eventually there was a cause.
So would that be, this is different, but would that be like two systems? Like would the wave be one system and then me pulling the wave be another? No.
I see what you're saying. I would talk about the Kevin rope gravity system, if we're talking about system, because you're in there, you're applying energy. You know what I mean? Okay. That sort of system analysis we don't normally talk a lot about when we're talking about waves and stuff like that. In the way that we did with work, energy, and power. Okay. But if we would say that the energy was transferring from Kevin's chemical energy in his body to the kinetic energy, right? And then that was in his hand, and that was transferring to the kinetic energy of the rope. Okay? So even when this particle starts falling, okay, that's just because you've got tension this way, and if you add those two vectors together, then it's going to be pulling it down. Okay? Wave on a string is a transverse wave. We saw that. Once started, the pulse continues to move because of the internal dynamics of the medium. Y'all saw that it was the tension in the rope which caused that caused that wave to move. Let's go ahead and see if we can analyze this real quick. Here we have a wave on a string. It's traveling to the right. At this instant, what's going on with the Kleenex that's tied right there? Okay, is this guy moving up or is he moving down? Go ahead, I'll give you 30 seconds to commit to an answer while I take attendance.
You're right, it's going down. Yeah.
Or is it moving left or is it moving right?
That's what I'm doing.
Or is it just hanging out right there and not moving at all?
Oh yeah, because it doesn't get ready. Because it doesn't move that way.
Just look at it.
All right, what do y'all think?
Watch it.
I thought
Down.
down.
Isn't it moving up? Down.
Down.
Next slide. Moving up.
Oh,
This wave is
wave goes
moving
up.
this way. So as a result, as this wave crest starts to hit this point right here, it's going to yank it up. Okay?
I need to like.
that makes sense.
So imagine the waves are traveling this way, okay? This part, this guy right over here to the left of him, he's pulling him up because as this wave travels this way, it's gonna go
That
pulled
makes
up, pulled up, pulled up. This guy gets pulled up, this guy gets pulled up, this guy gets pulled up, pulled up, pulled up, pulled up. And then it starts to pull it down. Alright? If you've ever had a speaker blow out, okay, break or whatever, normally what happens, we'll talk about that. I guess I should tell you how a speaker works. There's a magnet, you send electricity through the magnet that makes the magnet move back and forth, and as that magnet's moving back and forth, there's this, the speaker part is like just hanging out here, and it can go, it can move back and forth like that. It's got a little bit of little flexible material here on the outside that allows it, so what it does is it actually pushes the air, and then sort of pulls back, and then pushes the air and pulls back. And it goes back really, really, really fast, and it goes back and forth fast enough, and you can get that air to be moving, and then what we hear is a sound. And it can sound really cool. It can sound like your music, depending on how fast it goes. And so sometimes, if it goes back and forth so long, this little, it's kind of like an elastic material that goes around it, and kind of like a, well, it's very much like elastic. If it gets old, dried out, gets brittle, then that stuff can crack and then fall out. And sometimes if you have a speaker, then you start seeing little pieces down here. Like when I was hanging out with my friend, and we got his parents' huge speaker boxes out of the attic, and we cranked it up to 11, and the speakers moved back and forth, and all of a sudden we started to see little like styrofoam, little elastic pieces on the ground. Like, what's going on? And we were literally blowing out those pieces of the speaker surrounding there, and then so then this middle part here, which is moving back and forth, but it wasn't moving all of the air all together, and so it sounded really weak, and there was no bass, and we ended up throwing those little cabinet speakers away.
We're listening to Space Odyssey.
What's that?
We're listening to Space Odyssey.
I cannot remember what we were listening. Whatever my next door neighbor's music was, he had some weird tastes. So this is what happens. The speaker pushes the air molecules, like I was saying, and that causes a compression wave of those molecules to go through. We'll talk about this a lot more. But the idea is, what type of a wave does this look like? Where? Yeah, it's longitudinal. Okay. Weird, because when you think of sound, normally you think of something kind of like transverse wave. Yeah, it's actually a longitudinal wave. Now if you were to graph it, it would look, you could make it graph like a sine wave. Okay. The wave speed, so how fast it's going, does not depend on the size or the shape. It didn't matter if you were out there going like this, as if you're huge amplitude, or whatever, or just kind of going like this. Actually, how fast and how far the wave goes just depends on the medium. It just depends on if that string or spring was tight or loose, if there's a lot of friction or not. That's what makes the difference. Okay. If you're talking about a string, then it's going to be based on this, the linear density. Okay, so you've got a thick string, thin string. There's a formula here. It's not on your AP formula chart. That's okay. It's related to the tension and that mu, the linear density value. Go and turn your paper over. Go and answer that question there real quick. And the next one, 15.1, 15.2.
Will it be the same?
Alright. Which one is true, the velocity of A or velocity of B? What do y'all think? Which one's going faster? A or B? A with the small amplitude, B with the large amplitude? Same, right, because it doesn't depend on the amplitude, it depends on the properties. Alright, let's go and watch this fun video on waves to wrap things up.
Oh, we can't hear you, Mr. YouTube.
Wave is a disturbance which travels from one place to another, carrying energy but without carrying material along with it. Many waves have a characteristic speed. The size and shape of the disturbance does not affect how fast it
So they're all
travels.
going the same speed.
This allows us to talk about the speed of sound, or the speed of light. The amplitude of
Okay, he's telling us a million things at a time here. Do you see what I'm saying? Like the shape of it, whether it's like a triangle down or like up and a down, like a sine wave, or like this weird kind of like sharp thing with curve. Y'all see how they're all traveling the same speed? Yeah.
fast it travels. This allows us to talk about the speed of sound, or the speed of light.
So that's why we say the speed of sound it's always the same no matter how loud or how soft you're talking. Same thing with light. Doesn't matter if it's a high amplitude, low amplitude, high frequency, low frequency, it's all traveling at the same speed.
But temperature does change it, right?
Yes, temperature does change the speed of sound. Because sound is, what does the speed depend on? The medium. What's the medium for sound? Air. So you change the property of the air, temperature,
Oh, you change the air.
then you can change the speed.
The amplitude of a wave is how far from equilibrium it extends.
There's different amplitudes.
Harmonic waves, or sine waves, form a regular repeating pattern. The frequency of a harmonic wave corresponds to how many times each second a particular spot goes through its repeating cycle of motion. The corresponding wavelength is the distance over which the pattern repeats.
I don't like it.
The distance
What was that?
It's not
The point
moving and I don't like it.
Yeah, right? But
is just moving up and down.
it should, does that solidify it there for you? The Kleenex,
so
just
the
move it up
repeating
and
pattern in
down?
space and the time for each cycle are related to each other through the wave velocity. The time it takes one full wavelength of the wave to pass a given point is the same as the time it takes that one point to go through one full cycle of its motion. Thus, for each harmonic wave, the product of the wavelength and the wave's
We'll look
frequency
at that formula
is equal to the
more
wave
throughout the
velocity.
chapter. It's super cool formula.
So a wave with longer wavelength must have a lower frequency.
Oh.
Still traveling same speed.
Shorter wavelengths have higher frequencies.
Autobots, roll out!
Alright, today we talk about waves. Alright? Tomorrow, 15.3, we'll look at some graphical representations of waves.
Remind me of like
Snapshots. Also, we'll watch a couple videos on waves.
the water.
Oh, yeah.
Some surfing waves.
Could you open my personal, please?
Sure.